I'm Kathleen Anicolti Lagipo, and I will be discussing Einstein theory of relativity, specifically focusing on special relativity and time dilation. Albert Einstein introduced the theory of relativity, which changed how we understand space, time, and gravity. The theory is divided into two parts: special relativity, published in 1905, and general relativity, introduced in 1915. Special relativity deals with objects moving at extremely high speeds, especially near the speed of light. One of its key ideas is that time and space are not fixed, they stretch or shrink depending on motion. The main concepts of special relativity include time dilation, where time slows down for objects moving super fast, length contraction, making moving objects appear shorter, and mass energy equivalence, expressed by the famous formula E equals mc squared, shows that mass and energy are connected. A famous example of time dilation is the twin paradox. Imagine two twins. One stays on Earth while the other travels in spaceship close to the speed of light. When the traveling twin returns, they will be younger than the one who stayed. This is because the time moves slower for objects traveling at high speed. Special relativity also has real-life application. For instance, GPS satellites orbiting Earth move fast enough to experience slight time dilation. To maintain accurate location tracking, their clocks are regularly adjusted. In particle accelerators, scientists observe that particles moving near the speed of light experience time more slowly, which confirms Einstein's theory. Overall, special relativity reshaped how we view the universe. It revealed that time and space are flexible, not constant, and continues to influence modern science from space exploration to time travel theories.
Einstein's theory of relativity has two parts. Special relativity, which was made in 1905, shows that time and space are relative with key effects like time dilation and length contraction. General relativity, which was discovered on 1915, that explains gravity as the warping of space-time by massive objects. Examples of time dilation. An astronaut traveling near the speed of light will age slower than someone on Earth. This is confirmed by atomic clocks on fast-moving satellites. The impact is relatively crucial for GPS, black hole physics, and particle accelerators shaping modern science and technology.
Hello, I'm Sabrina Simultane. Now let's talk about general theory. Gravitational lensing is a phenomenon predicted by Einstein's general theory of relativity, in which the gravity of a massive object bends the path of light passing nearby. This bending acts like a lens, magnifying, distorting, or multiplying images of more distant objects behind it. How it works. General relativity describes gravity as the curvature of spacetime caused by mass and energy. Massive objects bend spacetime, and light, following the shortest path through this curved spacetime, is bent. The amount of bending depends on the mass of the lensing object and the distance involved. Strong lensing creates multiple distorted images. Weak lensing causes subtle distortions. Microlensing involves short magnification from smaller objects. Observational evidence. Strong lensing is seen as multiple images, arcs, and instant ring around large objects such as galaxy clusters. Weak lensing is detected statistically by examining the shapes of multiple galaxies to reveal subtle shears. Microlensing is observed as temporary changes in the brightness of distant stars. These observations confirm Einstein's prediction and are used to study dark matter and distant galaxies.
The Einstein's theory of relativity, space-time, is a unified concept that combines space and time into a single four-dimensional continuum. It's like a fabric that it's woven together by gravity and objects move through his fabric. This differs of Newtonian physics, which views space and time as separate and absolute, a three-dimensional, unchanging, and absolute background. Reliability, however, states that space and time are relative to the observer's frame for reference. Newtonian frame is of reference. Newtonian physics gravity is a force that acts between objects with mass. In relativity, gravity is a manifestation for a culture of space-time used by mass and energy. It's the same for all observers, an independent and absolute flow passing at the same rate continuum where space and time are intertwined. Space and time are not independent but are relative to the observer's motion. And gravitational Newtonian physics assumes absolute space and time, meaning they are the same for everyone. Example: imagine a scratch sheet of fabric. If you place a heavy ball on it, it will wrap the fabric, creating a dip. Now, if you roll a marble across of fabric, it will follow the curved path due to the warp caused by the ball. This is analogous to how massive objects like stars wrap space-time, causing objects to follow curved paths which we perceive as gravity.